Good morning. In the previous lecture, we have seen the analysis of a portal frame without any sway. Today's class, we are going to see the analysis of a portal frame with sway displacement. Sway displacement means lateral displacement. I mentioned earlier, if the frame is having any sort of irregularity or it is not having any sort of unsymmetry in moment of inertia of columns varying or unsymmetrical length of columns, varying length of columns, or if there is load from the side or there is lateral load, in all these conditions the frame will be subjected to sway displacement or lateral displacement of columns will occur in addition to the rotation of joints. So here I am going to discuss an example like this. A portal frame, all the three elements are of the same length, 16 meter, but there is a load 100 kilonewton acting from the side, or the column B, AB is subjected to a lateral load of 100 kilonewtons. So as such, it will be having, in addition to the rotations, in the previous example we have marked D1, D2, D3, D4, the rotations of the joints. Along with that, there will be having the lateral displacement of the column, and the displacement of the column AB and DC will be the same. That is, if there is a force acting on this, the column will undergo, it will deflect like this. So this delta, the displacement at the top of this column AB and the displacement at the column DC will be the same. So I have to mark only one coordinate, D5, as the lateral displacement. So mark from one node, all the nodes, 1, 2, 3, 4 nodes, you mark D1, D2, D3, D4, and at the top beam level, you mark the axial displacement of the beam or the lateral displacement of the column, sway displacement of the column as D5. Now what are the known boundary conditions here? In this, the support A and support D are fixed. So this D1 slope at A and slope at D will be 0. So the known boundary conditions are D1 equal to D4 is equal to 0. So what are the remaining unknown displacements? Unknown displacements are D2, D3 and D5. So unknown are D2, D3, D5. So I can write the first step, degree of freedom or kinematic indeterminacy of the structure are the possible independent displacements in the structure, that is equal to theta B, theta C and delta, or it is 3. The degree of freedom is 3, theta B, theta C and delta, but I will mention in the example as D2, D3 and D5. So that is the first step. So you mark the coordinates from one end to the other, all the slopes. Together with that, mark the displacement of the top story or the displacement of the column at the top edge. Mark the known boundary conditions. So the remaining unknowns are 2, 3 and 5. Now you split up into elements. So the first element, at the first element it is having D1, D2 as well as the displacement D5. So the coordinates for the first element AB are 1, 2, 5. For the second element it is actually 2, 3 and 5. But since the axial deformation of beams is neglected, we don't consider that D5. We consider it as an element with rotational coordinates 2 and 3 alone. 5 becomes axial displacement of the beam, which is usually neglected because the axial force in a beam or the axial displacement in a beam does not contribute to the bending moment or shear force values. So we neglect the axial deformation in the beam. Now coming to this CD element, it is having 3, 4 and 5 displacement. So columns are having 3 coordinates and the beam is having only rotational coordinates. Now we have to develop the element stiffness matrix element by element. Now we consider element by element. The first element AB is having coordinate 1, 2, 5. It is having element D1, here it is D2 and D5. So what is the stiffness matrix? We don't have a ready-made formula with us for that. So we'll derive the stiffness matrix for that element with 1, 2, 5 coordinates based on the principle of stiffness influence coefficient or the physical approach. What you have to do is you apply d1 equals 1, apply unit displacement here, arrest all other displacements. So this beam will bend, which is clockwise. So it will bend like this. So this is equal to 1. You give unit displacement at this point. At that time, arrest the other displacements. So by giving unit displacement here, what is the moment from there? We have studied earlier. By giving unit displacement here, the moment at this point is 4ei by L clockwise moment. The moment at this point is far end. It is 2ei by L. So together, it is 4 plus 2. 6ei by L is the clockwise moment. To produce anti-clockwise couple, here it should be left. You stand here and look in this direction so that it will be a beam at this end 4ei by L, this end 2ei by L. So totally 6ei by L is the clockwise moment, anti-clockwise left to down, and here it is up. Each of these values will be 6ei by L square, 6ei by L square. So this is the physical approach we have seen in the first part of the video. By applying unit displacement here, the moment here will be 4ei by 2ei by L, and these forces will be 6ei by L square. Now I can write down the stiffness matrix for element AB is equal to ei into what is corresponding to coordinate 1. Corresponding to coordinate 1, it is 4ei by L. So I have written 4 by L. Corresponding to coordinate 2, the moment is 2ei by L. And corresponding to coordinate 5, the corresponding to coordinate 5, this is the 5 direction. The force is 6vi by L square, but is in the opposite direction of 5. So it is minus 6ei by L square. I'll repeat once again. The force in direction 1, 4ei by L. Force in direction 2, 2ei by L. Force in direction 5 is 6ei by L square. So opposite to the direction 5, so minus 6 by L square. That is the first column. By applying d1 equals 1, what are the values? That will be in the first column. Now coming to the second, you apply d2 is equal to 1 here. At that time, arrest the other end. So it bends like this. You apply unit value here. So the moment developed here, it is 4ei by L. In the far end, it is 2ei by L. So totally 6ei by L. So to counteract it, there will be left to down, right up. 6ei by L square. 6ei by L square. So what will be the value? By applying d2 is equal to 1. Force developed in direction 1. In the direction 1, it is 2ei by L. In direction 2, it is 4ei by L. And direction 5, it is minus 6 by L square. Write down the vertical form. Now next one is d3 is equal to 1. D5 is equal to 1. So that is in this, you apply unit displacement in this direction. Apply d5 equal to 1. Arrest the other end. So it will deflect like this. So what is the moment developed here? You stand here and look at the right support sinks down. See, it's anti-clockwise moment. 6ei by L square. Here also anti-clockwise moment. 6ei by L square. So to counteract it, there will be clockwise coupled. Clockwise left up, right down. 12ei by L cube. 12ei by L cube. So by d5 is equal to 1, by giving d5 equal to 1, in the first direction it is minus 6 by L square. In the second direction it is minus 6 by L square. In the direction 5, the same as that, it is 12 by L cube. So this is the stiffness matrix for this column element with coordinates 1, 2 and 5. This is the derivation part. In the examination, you need not write down the derivation. You can remember this formula just like this. See, we know when there is rotation around, it is 4A by L, 2A by L, 2A by L, 4A by L. Together with that, see, you write 6 by L square, 6 by L square minus 6 by L square, 6 by L square, and the diagonal element is 12 by L cube. It's an easy way of remembering. Otherwise, the derivation is like this. 4 by L, 2 by L, 2 by L, 4 by L is known to you. 4A by L and 2A by L for a beam with rotation along. Along with that, there will be elements 6 by L square minus 6 by L square here, minus 6 by L square, and the diagonal element is 12 by L cube. So that is the stiffness matrix for the column AB. So we have to remember this. For the column element AB, 1, 2, 5, the stiffness matrix is 4 by L, 2 by L. So this is 1, 2, 5. Here also 1, 2, 5. Now we just substitute the values for the column element AB. The length is 16 meter. So you calculate what is 4 by L, 0.25. 2 by L, 0.125. 6 by L square is 0.0234. And 12 by L cube is 0.003. Just substitute these values, you will get KAB is equal to, stiffness matrix for AB is equal to EI into 0.25, 0.125, 0.125, 0.25 minus 6 by L square minus 0.0234 minus 0.0234 minus 0.0234 minus 0.0234 0.003. The stiffness matrix for the first element, and you have to write the numbers 1, 2, 5. 1, 2, 5. Now, similarly, write the stiffness matrix. I will write the similar elements CD. For the element CD also, this column, coordinates are 3, 4, 5 and the length is same, 16 meter. So I just repeat it for this element CD. I am not going to recalculate it. Everything remains the same. So it is 0.25, 0.125 minus 0.0234 minus 0.0234 minus 0.0234 minus 0.0234 0.003. Since the length and moment of inertia are same for that member also, I can write it very easily similar to that. Then what is the difference? The coordinate numbers. You have to mark the coordinate numbers. That is very important for assembling it. The coordinate numbers are 3, 4, 5. 3, 4, 5. That is for the column CD. Now one element is left, that column, that beam element BC. For BC, coming to element BC, we are going to write the element stiffness matrix for the element BC. BC is this element. It is having only D2 and D3. Length is 16 meter. So the stiffness matrix for BC is very simple. We have seen EI by L into 4224. So EI by L into 4224 or EI by 16 into 4224. It will work out to EI into 0.25, 0.125, 0.125, 0.25. And what are the numbers to be written there? For this element it was 1, 2, 5. For this it is 2 and 3. 2, 3, 2, 3. Thus we have got the stiffness matrix for all the elements. The next step is to properly assemble them together. Post the elements in the correct locations in the final stiffness matrix. So next step, structure stiffness matrix. K EI into. Here you have to be very careful in posting the elements. First of all, what you have to do is, we know this support D1 and D4. They are fixed support, so D1 is equal to 0 and D4 is equal to 0. The final stiffness matrix will be having only 3 degrees of freedom, and corresponding to 3 degrees of freedom, 2, 3 and 5 will be having elements 2, 3 and 5. So D1 is equal to 0. So from the first element, you delete first column and first row. Then from the element CD, D4 is equal to 0. So you delete column bearing number 4 and row bearing number 4. So these much elements should not come into this. Now let us post it from one element to the other. See the first element, AB. First element, we have the element starting from location 2, 2. In the location 2, 2, it is 0.25. And the next is 2, 5. In the location 2, 5, it is minus 0.0234. Here 5, 2. In 5, 2 location minus 0.0234, and the 5 location 0.003. So post the elements from the first element in locations 2, 2, 2, 5 and 5, 2, 5, 5, 5, 2, 5, 5. Second element BC, from the second element BC, in location 2, 2. In 2, 2 there is 0.25. So 0.25 in location 2, 2. So this is location 2, 2. There is another 0.25. Next is 2, 3. In 2, 3 there is 0.125. Then 3, 2, 0.125. And 3, 3 it is 0.25. So these are the 4 entries from the second element. Now coming to the third CD, in location 3, 3 there is 0.25. 3, 3. 3, 3 there is 0.25. Then 3, 5. 3, 5 minus 0.0234. 5, 2. Third element 5, 3. In 5, 3, 5, 3 minus 0.0234 and 5, 5 0.003. So the one with red color is from the CD element. It is 0.25 in 3, 3. In 3, 5 0.0234. Then 5, 3 0.0234, and in 5, 5 0.003. So you have to add it at this location. It will become 0.5. Here also it is 0.5. Here 0.006. See. So the stiffness matrix which are going to get is this final stiffness matrix K is equal to EI into 0.5, 0.125 minus 0.0234, 0.125, 0.5, 0.0234 minus 0.0234 minus 0.0234, 0.006. This is corresponding to 2, 3, 5. So see, the stiffness matrix is symmetric, diagonally dominant. It's a square matrix, 3 degrees of freedom. It's a 3 by 3 matrix. So we have arrived at the stiffness matrix for the structure. Next few steps are similar to the previous example. Arrive at the load vector, solve the equation, and then calculate the final moments. Next step is to arrive at the load vector. So you consider element by element. First element AB. Before that, you have to see what is P0. P0 is externally applied loads at the nodes. In this example also, at nodes A, B, C, D, there are no external loads. So this P0 in this case also 0. There are no externally applied loads at the nodes. Now coming to the fixed end moment vector PF, consider element AB. You consider element AB. Element AB was having a load of 100 kilonewton acting at its midspan, and it was 8 meter, 8 meter, these two lengths. Now look from here, it says similar to a beam subjected to vertical load at the center. The fixed end moment here is anti-clockwise, WL by 8. So it works out to 100 into 8 by 100 into 16 by 8. It is equal to 200. So this moment is 200 kilonewton meter. Similarly here it is clockwise moment, 200 kilonewton meter. So the fixed end moments are minus 200 plus 200. Now due to this 100 kilonewton load, there will be support reactions. What about the support reactions? This load is acting like this, so this reaction will be 100 by 2, 50 kilonewton. This reaction will also be 50 kilonewton. So let us write the fixed end moment vector for that element. This coordinate was 1, PF 1. This was coordinate 2, and this was coordinate 5. For the first element, corresponding to coordinate direction 1, there is minus 200. Corresponding to coordinate 2, it is plus 200. And corresponding to 5, 5 is towards right, this is opposite direction, so it is minus 50. So the fixed end moment vector is minus 200, 200, minus 50. I'll repeat once again, this is the one direction, the moment is minus 200 anti-clockwise. The 2 direction, so it is plus 200. This was the 5 direction, it is opposite, so it is minus 50. Now coming to element BC. There is no load in the question in this element. So the coordinates were 2 and 3, corresponding to 2 and corresponding to 3. There are no fixed end moments because that span was not having any load. Now similarly, corresponding to this third element CD, this vertical element, there is no load in this column. So the coordinates were, this was 3, this was 4, and this was 5. So corresponding to 3, corresponding to 4, corresponding to 5, in that element CD, the fixed end moment vector is 0. Suppose in the question there was some load in the span, then we have to, similar to this case, we have to arrive at it. So now you give for the structure. For the structure, the fixed end moment vector is equal to, as earlier we know the boundary condition, PF1 is equal to 0. PF1 is no, the coordinate displacement in direction 1 is 0, so we don't require that. Similarly, coordinate direction 4, D4 is equal to 0, so we need not require the amount corresponding to 4. So we need only PF 2, 3, 5. Because 3 by 3 matrix, to solve the matrix we need the load vector corresponding to 2, 3, 5 coordinate directions. Corresponding to 2 from the first element, it is 200. Corresponding to 5, there is minus 50 from the first element. From the second element, 2 as well as 3 are 0. So here plus 0, here also 0. From the third element, corresponding to 3, 0 and 5 also 0. 3, 0 and 5 also 0. So add it from all the elements, you will get 200, 0, minus 50. So the load vector is 200, 0, minus 50. Now P is equal to P0 minus PF. P0 is 0. This is PF. So 0 minus 200, 0, minus 50 will work out to minus 200, 0, 50. So the load vector is equivalent joint load vector. P for this structure is minus 200, 0, plus 50. So next step is solve the equation K into D is equal to P. So fifth step, solve K into D is equal to P. Solving, we will get D2, D3, D5. As you solve the 3 by 3 equations using the calculator, you will get the answers minus 51.46, 481.37, 10,007.98. These are the answers of displacements. So the displacements answers are, this one is corresponding to theta B, 51.46 by A radians. This is theta C, and this is the sway displacement. The resulting displacement values we have got. Now coming to the last step, the final moments are arrived at as fixed end moment vector plus element stiffness matrix into displacement vector. Consider element by element. First element AB. The coordinates were D1, D2, D5. This was A and B. So corresponding to coordinate direction 1, I will be getting the answer MAB. Corresponding to 2 direction, I will be getting the force MBA. And corresponding to D5, I will get the axial force in the beam at the point B, FB. That is equal to fixed end moment vector. Fixed end moment vector for that particular case, refer back to the previous step. It was minus 200 plus 200 and minus 50. Fixed end moment vector plus stiffness matrix of that element. Stiffness matrix of the first element in the first step, 0.25, 0.125, 0.125, 0.25, minus 0.0234, minus 0.0234, minus 0.0234, minus 0.0234, 0.003. This was the stiffness matrix for the first element, and it was bearing numbers corresponding to coordinates 1, 2, 5. So you have to multiply the stiffness matrix with the corresponding displacement vector D1. D1 is equal to 0. D2, we have got the answer minus 51.46, and D5 10,007 into 1 by AI. After doing this multiplication, you will get the answer minus 440.68, minus 47.17, and minus 18.76. Now coming to the second element. BC, it was D2, D3. Corresponding to 2, I will get MBC, and corresponding to 3, I will get MCB. That is equal to the fixed end moment 0 plus stiffness matrix for that element AI into 0.25, 0.125, 0.125, 0.25. The numbers at the top were 2, 3. It was 2, 3. So you multiply with D2, D3. D2 is minus 51.46 and D3 is 481.365. So you get the result as 47.17, 113.85. Now similarly coming to the element, third element, CD. It was a vertical element. This end it was 3, this end it was 4, and displacement 5. This end is C, this end is D. So what are the values we are going to get? Corresponding to 3, we will get MCD. Corresponding to 4, we will get MDC. And corresponding to 5, we will get the axial force in the beam at C, FC. So that is equal to fixed end moment. There was no fixed end moment for that. Plus stiffness matrix, the same as this EI into, I'm not going to write that. It was same as this matrix, and the numbers of the top were 3, 4, 5. These numbers were 3, 4, 5. I'll write it 0.25, 0.125 minus 0.0234. Similar to this, multiply with D3, D4, D5. What was D3? D3 was 481.365. D4 was 0. And D5 works out. D5 was 1007.98. So that you will get the answer as minus 113.85 minus 174.01 and 18.75. These are the bending moment values. We can check whether the answer is correct because MAB, MBA. MBA is 47.17 and MBA plus MBC. MBC is plus 47. Should be 0. MCB 113.85 and MCD should be minus 113.85. Axial force at B is minus 18. Axial force at C is plus 18. So the total axial force at that joint is 0. Axial force in the beam is 0. Okay, now we have got the bending moment values. You have to plot the bending moment diagram. Let us see how to draw the bending moment diagram based on these values. Okay, now the last step is we are going to draw the bending moment diagram. I have rewritten the values of bending moment diagram here for each element. So to draw the bending moment diagram, draw the structure A, B, C, D. From the first element we got MAB equals minus 440.68. That means anti-clockwise. A to B anti-clockwise. So it comes in this direction. So it is 440.68. So to some scale you mark 440.68 kilonewton meter in the anti-clockwise direction. MBA is minus 47.17. So B to A, it's also anti-clockwise in this direction. It is how much? 47. So mark 47. From here to here, mark 47. Join these two. Next span BC, MBC 47.17. So B to C clockwise. So comes down. 47. Mark here. 47.17. MCB 113.85. C to B. It is 113 clockwise. So mark 113.85 at this point C. So join these two. Coming to last, MCD minus 113. C to D minus. So it is anti-clockwise. 113.85. This is clockwise. And here MDC is minus 174. D to C anti-clockwise. Minus 174 kilonewton meter. Join these two. So this is the support moment diagram. Now superimpose the span moment diagram or the simply supported bending moment diagram. In this span there was a load of 100 kilonewton at the middle point. At the midpoint there was a load of 100 kilonewton. So due to this there will be a bending moment diagram like this, and this value will be WL by 4. 100 into 16 by 4, it will be 400 kilonewton meter. So this value is 400. Now we have drawn the support moment diagram and superimposed the span moment diagram. So the resulting is, or the resulting, this portion here, this much portions here, hatch. So this portion is we call hogging moment. Outside this portion is sagging. This is also in sagging. This entire is sagging. Above the line it is hogging. Here it is above the line hogging. This portion is sagging. Portal frame, you stand inside, look in this direction. So this is inside, outside. Outside portion hogging, inside portion sagging. Outside hogging, sagging. So this is the final bending moment diagram. So with that we have completed the analysis of rigid joint frames. That is taken the example of a portal frame without sway as well as a portal frame with sway. Thank you.